Welcome, everyone. Thank you for joining us today on this month's University of Wisconsin Division of Extension Badger Dairy Insight. Today, we'll have a topic called Leveraging Digital Technologies to Improve Management Decisions on Dairy Farms. Badger Dairy Insight is a monthly webinar series offered on the third Tuesday of each month. It provides the latest research, dairy-based information to improve animal welfare, breeding and genetic selection, automation and modernization, and nutritional decisions for producers, dairy workers, and managers, along with agricultural professionals. So welcome. My name is Angie Allness, Extension Educator for the University of Wisconsin Division of Extension, and my colleague and I, Ryan Sterry, are your hosts today. We hope to provide this opportunity as an informal decision information discussion on today's topic. As this is a webinar format, please add any questions or comments as we move along through the Q&A button at the bottom of your screen. And the presenter also noted that if you have to jump off early and you want a question to be asked, he will answer those questions at the end of the webinar. As this webinar is being recorded, we'll provide a link of the recorded webinar to you within a week in hopes of sharing with others you work with. So without further ado, I'd like to introduce our first speaker, or our speaker today is Dr. João Dórea, and he will speak, like I mentioned before, on leveraging digital technologies to improve management decisions on dairy farms. Dr. Dorea is an assistant professor in precision agriculture and data analytics at UW-Madison. He obtained his BS in agronomy from the university in Brazil, a master's and PhD degree in animal science from the University of São Paulo in Brazil. Dr. Dorea spent 2 years coordinating dairy and beef research in Latin America, and in 2019, he was hired as an assistant professor in the Department of Animal and Dairy Sciences here at the University of Wisconsin-Madison. Dr. Dorea developed research focused on digital technology and predictive analytics to improve farm management decisions. His research group is interested in large-scale implementation of computer vision systems, wearable, and other sensors to monitor animals on livestock farms. Examples of application include the use of digital technologies to monitor animal behavior, growth development, and social interactions. His innovative research program has been extremely well accepted by the livestock industry and scientific community. So we're really excited. Dr. Dorea, if you want to take it away.
Thank you very much. Thank you for the introduction, Angel and Ryan. Thank you for the invitation. And good morning, everybody. So today I will talk about the digital technology, as Angel mentioned, how we have used that to improve management decisions. So I'll show a few examples and why we are interested in developing those technologies for the dairy industry. So if you think about technology, and we look at the progress that genomics had in the dairy industry over the past years, it's very clear that technology can really make progress and advance our production systems in agriculture as a whole, but specifically here today in terms of dairy production. As you can see, the amount of milk production per cow increasing from 1931, and the number of cows decreasing over time from 1931 up to 2021. And so we are producing more milk and with less fewer cows. And so that shows the progress in management, of course, right? We're managing the herds better, the cows better, but we also have a tremendous impact of genomics. And now we see all the omics, as we call, making progress as well, and people more interested in doing research and understanding how that can bring some advance and improvement in the dairy sector. But one interesting component of the advance of genetics and genomics was that the cost to genotype the animals drastically decreased over time. So as you can see here, in 2001 and 2002, the cost of genotyping animals was high. And then as you get to 2007 and 8, these keep decreasing dramatically up to 2021. And so as this is a good illustration to show as time goes on, technologies advance and the cost of a lot of those technologies keep decreasing, which make them easier to adopt and more attractive to be adopted, because now the cost to use this technology is really low, and the return on the investment of this technology keep getting better and better as the cost of the technology decrease. And so if we look for this particular example here, where we have the number of cows being reduced and the amount of milk being produced higher and higher, and a lot of these because of better management and genetic progress, we right now have a bottleneck on this genetic progress, for example, that is related to the phenotypes, right? So it was easy to collect milk and milk components in the past and make progress on that particular area. But now, as we aim to improve behavior, welfare, animal health, we do need to collect those measurements at the animal level. And that's what we call the phenotypes, or the traits that we want to improve, right? And in order to make improvement in that particular trait or that particular phenotype, we do need to collect them. And collect them in large scale is really difficult. So if you imagine dry matter intake or feed efficiency, you want to select for feed efficiency, you need to measure feed efficiency in every single animal. And so measuring these in thousands of animals, we require some work, and it's expensive and it's labor intensive. And that's the area we also work, developing technology so we can measure those phenotypes, and from traits or phenotypes that were not measured before, and then we could use that to make genetic improvement and to, of course, make better management decisions at the farm. And so our lab is really interested in develop sensing technology for phenotyping. And as I said, phenotyping is this animal level information that we are interested in. And with that information in our hands, then we can integrate these with all the information related to price and crop and the feed that we are feeding the animals. And we can also use that information for genetic improvement. And the only way we can collect large scale data for at the animal level is using sensors. Right? There is no way we can keep watching animals eating and say, okay, eating time of this cow, 200 minutes, eating time of the other cow, 300 minutes. That's impossible. We cannot sit there and keep watching cows and taking notes. The only way we can measure this in large scale is by deploying sensing technology and monitor this in large scale. Now, this will vary from using robots or using wearable sensors or using drones in grazing systems or microphones or cameras. And so this is all necessary in order to obtain phenotypes or traits related to animal behavior, infectious disease, body composition, methane emission, feed efficiency, feed intake, social interaction, all these traits that people may have interest and that are important from the genetic standpoint and for improvement, and also from the management standpoint. And so as we as we collect that data, this will have a positive impact in farm management. So for example, if I have sensors that can give me an alert that this cow will get sick, this is extremely important. And so these will have an impact on profitability and economics at the farm. And long-term, collecting that data at the individual animal level will bring us will help us to better select animals, genetically speaking, that will stay in the herd and make improvement for that particular trait that's been selected or measured. On top of all of these, it's been really hard to hire people in all sectors and in agriculture, and that industry is not different. And so maybe people don't want to stay as in the past at the farm working with the animals. And so the technology can really help on that aspect as well. So what do we need in order to build this technology and start developing? We definitely need what we call capacity building. We actually are having that or developing these at UW-Madison. So we have farms with cameras deployed. We have more than 100 cameras deployed at the farm where we try to track animals for behavior, body composition, growth development. And so this is extremely necessary in order to have robust systems that will be developed and commercialized by companies in the dairy industry. So today, I want to show you few examples that we have, they go in our lab to develop related to farm management decisions, and they are related to nutrition and health, and how we can use, for example, in today's example, computer vision and image analysis to improve animal monitoring, and with that generate some decisions that could make our systems a little more efficient. Okay. So this is a picture of our research farm. I will show you an example of what we have deployed there. We have run some experiments with that infrastructure that we built. And then we have in our farm these cameras installed. They are depth cameras, what we call them depth cameras. I will explain in a bit what it is. They are installed at the exit of the milking parlor. So every time these cows are leaving the milking parlor here, the camera will acquire pictures automatically of these cows. And these cameras, they generate regular pictures, as you can see here, like this, what I call this grayscale. It's an infrared picture. So it's a grayish, black and white, as you can see here. And then the same camera generates this depth image. So the depth image gives us the distance from where the camera is located to the animal in the picture. Okay, so each pixel here, each value on this image, will be the distance from where the camera is located to the object. So if you see here dark blue, it means that the distance it's closer to the camera. And then if you see this strong light green here, it means that this is far from the camera. And so we can have a 3D map of the objects in the scene when you use these cameras. Now, the way it works is every time the cows are walking out of the parlor, this camera will take pictures automatically. Will detect that is an object walking here in the lane, and then you acquire a sequence of pictures. Because we are not stopping the animal, it's all completely automatically the way the camera works. We're gonna have what we call bad image, and we're gonna have good images. And bad images are basically image where we have the cow cropped, no cow, two cows in the same image. And a good image is the image where we have the whole body of the cow, as you can see here. We wanna have a complete, the whole body, the complete body information of the cow within the image, in the image. And so in order to automate that process, we train a model that basically select what is a good image and what is a bad image. So every time you collect the sequence of pictures, the model will automatically collect the good image. As we collect the good image, another model that we train will find the pixels or that belongs to the animal body. Basically, we'll segment the animal body, identifying the pixels that are part of the body. By doing this, I remove the whole background. That's not important. It's a bunch of metal bars and concrete. I don't need that. I just need the body of the animal. And so this second model will segment the body perfectly. And then by segmenting the body, these will produce these two pictures. One, remember the infrared or the regular picture of the cow, and this depth image. Now they are segmented. They don't have background. So I have the perfect image of the cow for these two types of image, the infrared and the depth. Now, with that in hand, I can do several things, which actually it's the object of our studies, is I can run animal identification, for example, using the coat color pattern, like the black and white of the animal. And I can, for example, predict body condition score, body weight, body volume of this animal using the depth image here. So I'll show you more details about that. So my question you may have is, for example, how good is the model to identify cows based on the black and white, the coat color pattern here, right? And so we have this experiment with 92 lactating cows, and we achieve an accuracy of 96% to identify individual animals. So the model works very well identifying the animal based on this unique coat color. The cows will have a unique signature because the hosting cows, they're black and white, and this will work some sort of like QR code or barcode of each individual animal that we then can identify them using the cameras and the computer vision models that we train. The problem is, as you have Jersey cows, black Angus, or other animals that you have very similar or solid homogeneous coat color, then the model will get very confused. In this case, for example, imagine if you have 4 cows, these are 4 different black cows, hosting cows, but all black, and the model will get very confused to recognize them. So what are we trying to solve this problem? What we did was we did not use the black and white coat color to identify the cow, but we did use the body shape. Only the shape of the cow, the body surface, as a unique signature, a unique identifier to be used, and then we can distinguish and separate the individual animals using the body surface. Now, as we can see here, we test different body shape, body representations. I will not go into detail about point clouds and the type of things we tested, but what is important to mention here is that we achieve an accuracy or F1 score, in this case, of 0.8, meaning that the performance of the models were very good, distinguishing among different animals. We have a total of 40 animals here that we identify them based on the body surface only. And then an obvious question that I usually ask it is, okay, what is the animal is changing shape? What is like a calf or a heifer that is growing and the body surface is changing? So how these models would behave to identify the animals in the production system as the animal change shape. So in this particular trial here, we started skipping, we did this with calves from 2 weeks of age to 8 weeks of age. So the animals were really changing body conformation. And we started skipping 1, 2, or 3 weeks. And so we trained the models with week 1, and then we skipped 2, 3 weeks and got the animal older and tried to identify the animal when the body was already changed. And the model stayed, continued to predict well the individual animals, even in this short-term period where this interval that we had, so that the animal changed the body a little bit. So recently, we tried to do a little a more complicated identification. We skip 423 days, so almost 2 years of interval between when the pictures were acquired and when the animal was tried to be identified later on. So here, for example, you can see this is the animal really, really early on with 26 days average age. And this is the animal, 423 days of age, average age. So we try to identify them. So you can see, for example, the difference in body weight, 43 kilograms of these calves. And then we try to identify the animal with 426 kilograms. So it's a huge difference in body shape, in body conformation. And so, but what you want to do is, can I train a model when I have a baby calf? And then when this animal it's older, it's a cow, a lactating cow, if I need to recognize that automatically 1, 2 years later, can I do that? And so what we achieved was an accuracy of 72%, precision 0.76, recall 0.75, F1 score 0.73, which is very promising results given the huge interval that we are computing here. And the other thing we try to do is train a model that would receive pictures of animals that were not part of the herd before, and the model should be able to say, I don't know these animals. And so we include 14 new animals, and the model should say, this doesn't belong to my herd. And the model was 85% accurate to say, I don't know these animals. These animals were never here before. And so all these identification trials and experiments we have done with image, they are very important for connecting the phenotypes or the behavior, the intake, whatever we measure with the cameras with each individual ID. And it's also important for traceability. If you think about developing these for a regional level or for a national level, it would be incredible to have a picture of the animal at the first day of life, and then 4 or 5 years later, you can identify this animal no matter what the animal showed up. So that's the long-term goal of developing these identification systems based on computer vision cameras. Okay, so now that we have this pipeline, we are very interested in the body conditioning scores. Now that we can somehow identify these animals, let's look to change in body shape and how this can inform, for example, for early detection of disease in dairy farms. So if you go in the literature, you're going to find very similar prediction performance as we found here, where researchers have reported accuracy to classify body condition score between 81% or 96% in the 5-point scale body condition score. And these will vary depending how much error you assume. If you want to tolerate a 0.25 error in your classification, so from 3.25 or 3, if you consider them the same thing, then you get an accuracy of 81%. Or if you consider a 0.5 error, then you go to 96%. And this is very close to what is being reported in the literature. And so you can definitely use the cameras to classify the body conditioning score, given our results and other results that are already published. But we are not very interested on doing this at this point. Although we recognize the importance of a body conditioning score, you have the problem of being subjective. So I may think this cow is 2.5, you may think this cow is 3.0. And so there is all this disagreement may happen because this is a subjective measurement. So this is an example. I have this cow 21 days before calving or 14 days before calving. 3 evaluators look at the cow, not through the picture. They went to the farm, they saw the cow, and then they evaluate the cow as body condition score 4.0. And 7 days later, or 14 days before calving, 4.0 again. When we overlaid this image perfectly, then we saw a difference in body shape. So it's clear, was clear to us that there is a difference in body shape that our eyes cannot detect. And so the question that came to us is how can you use the depth image, how can you use the change in body shape to detect disease or to detect cows that get sick because of body tissue mobilization, and that by doing body condition score only would be difficult to detect. And so we then developed this trial. We did this in collaboration with Dr. Heather White. Was a very nice trial. We used 92 hosting cows. We collect prepartum image, wearable sensor data, and text, and I'll explain what the text was. And we measured those things, the image and the wearable sensors, 21, 14, and 7 days before calving. So we have these 3 time points, 21, 14, and 7 days before calving. And we collect blood samples after calving. So we then define a cow with subclinical ketosis based on the beta hydroxybutyrate, BHBA values above 1.0 millimole postpartum. So if the cow had that, we call this cow as a subclinical ketosis. And we collect 52,000 images of these cows, again, plus the wearable data for behavior, plus some text information that was in the software. And we use the prepartum, this is very important, we use prepartum data here to predict subclinical ketosis at the postpartum, okay? So this last time point here was 7 days before calving, and we are trying to predict the disease up to 14 days after calving. So you see that in the best case scenario, the distance between my last data point and the health event will be about a week or 8 days or something like this, okay? That's the best. And the worst will be even longer period between my last data point and the health event that may happen within these 14 days. Okay, so it was quite a task, but we are interested to do this early detection. So I won't go in detail here, but the way we process the image, we train a model using the depth image. These models are called, that we use convolutional neural networks. So basically these models will learn features about the body shape of these cows, and then we will extract 1,000 features, 1,024 features here using this convolutional process. We extract features from the body shape of the animal, recognizing parts of the body that are related to body conditioning score or to changes in body shape. And then by extracting features from this image, we look to where the model was putting attention on the body. So these are the gradients extracted from the model. And so you can see, depending the classification of the body conditioning score or the body shape of the cow, the model will put attention in different parts of the back of the surface of the animal. So then we extract these features that would represent the body shape of the animals from the death image, 21 days, 14 and 7 days before Kevin. And then we're gonna group all these features, and then we have what we call imaging features. We then collect wearable sensor data. We had collars on these animals, and these collect data. I explained, like eating time, visit duration, number of visits at the feed bank, total time, which is the eating time, total time spent at the feed bank, meal interval, rumination. All these behavior data were collected in the last week, 7 days before Kevin. And then we went to Dairy Comp, what was the software we were using, and we extract previous lactation information from these animals and notes about the animal that were put as a unstructured text. That's what we're calling here. So all these free text notes that you type, we type in Dairy Comp about the animal, we extract that and we use that as a predictor. And so this was a quite an interesting project, particularly for the analytic standpoint, because we're merging structured data with this tabular data, like behavior or with columns and rows and so on, with unstructured data which came from the text. So imagine a paragraph written, imagine you combining these with an Excel file to analyze. So it's in a simple way to illustrate, that's what we end up doing here. So again, that's the structured data I was mentioning. So we have the cow, you have days relative to Kevin, number of visits, eating time, meals, time duration, rumination, line time, etc. All these behavior being computed, and they are tabular, as I said, like structure, like a square, as you can see here. And then we obtain these nodes, as you can see, for each animal. So basically said, okay, the cow was a double OV-sync was using this cow. The cow was open. I did this. I used that. I collect milk spectrum from this cow. These are the responsible. Here I put my name and my student's name. So Rafael or João. Daisy milk, which pen this cow was. All these notes that are not very well structured in the system, we convert them into text. And so the text here is represented with the date and a sentence saying, the cow entered the herd as a fresh heifer on that date. This event happened in pen 26. And so we convert all these free notes, or the notes as are here, in this text sentence. And then we use a large language model to extract features from this text. And so basically these features were basically converting the text into numerical representation, and that now is tabular and is structure, and then I can combine these with my image features and my wearable sensor feature. So just in summary, we use this unstructured piece of information, we convert these into a numerical representation, so the text now became numbers, and these numbers were connected to the other numbers coming from the image and coming from the wearable sensors. So what we found was an accuracy, a F1 score of 0.68 and an accuracy of 76%, to early detect subclinical ketose 7 days in advance. So that was very promising results. When we evaluate the impact of adding unstructured notes or these text notes to the model, we observe an improvement in the model accuracy and F1 score. So there was relevant information in the text note that was added here. And usually this is not very considered or used in those traditional analysis, because it's just difficult to integrate free text, unstructured text with structured data set. So that was a very nice result we found, and very promising, with 76% accuracy to early detect cows that will get sick. Now, we do know that 21 days in advance it's not enough, and ideally we want to detect these even earlier. So we are running trials now where we are looking to 60 days before Kevin as a time series, and see how early we can detect cows that will get sick, so we can suggest or propose management decisions that could change the course of this cow that will get sick. In the previous example I mentioned now about the subclinical ketones, I showed you behavior from wearable sensors. Here is just a paper we published with behavior now, feeding behavior being monitored through cameras. So as you can see, we have every time the animal is going to visit the feed bank, we compare total eating time, visit duration, interval between visits and visits. And the way we do this is basically by identifying the individual calf. And if the animal crosses the head on the headlock, we place this bounding box, so the model detects the animal. And then by detecting every single individual animal that is coming to the feed bank, we then compute these metrics, which are total eating time, visit duration, and so on and so forth. And if you look, the correlation, the I-square between predicted and observed here, pretty high, showing that the models are a very has a good performance and can work quite well for behavior. And this is an example. This is an example here with not looking to individual animal, but looking to a group of animals. So these are, all the animals that are eating, lying, standing, and drinking in the pen. So here you're looking to the whole pen and not to an individual animal, which may have value as well by monitoring the management strategy or the management being applied at the pen level. Here's another example of things we are interested. We're interested in monitoring respiration rate using computer vision. So we have a camera that automatically detects the flank of the animal. So you can see this flank going up and down, up and down. And then this will search for another animal here and then get this flank going up and down. As you can see, the signal here is the signal of the respiration rate. So this raw signal is being converted to a frequency domain. So there's a lot of some mathematical functions being implemented here that will convert this to a frequency, and then we count the peaks, and we then determine what's the respiration rate of individual animal using a single camera. So here is the correlation between the predicted breaths per minute and observed. So you can see the respiration rates predicted and observed. So very good prediction. Here you have infrared and RGB. Basically, this is night image. Oops, let me put this back. This is night image, so that measuring respiration rate in the dark with the night vision of the camera. And this is along the day with RGB, which means like doing a color, regular picture. And this is the correlation between predicted and observed respiration rates. And so the last example I want to show you with the computer vision for management is using the computer vision for detecting lameness or mobility problems at the farm. And this is a big cause of economic loss in the dairy industry. It annually is over $11 billion and globally. And so the total cost can go up to 177 per case. And if you look to the worldwide prevalence, it's about 22%. So one lame cow, in every 5. And so the way the mobility score would be applied, it's by watching these cows walk and then look to some characteristics of the way the cow is walking or the mobility of the cow, and then you can assign a score from 0 to 3, where the 0 is a good mobility and 3 is a severely impaired mobility. This is really hard to do at the farm because you need to be there watching cows and tracking cows, and we know this is really hard to be implemented systematically. So some technologies have been some technologies have been proposed as pressure mapping system, where the cow is walking, and then based on the pressure the cow is applying to the mat, then you know if this cow has a problem or not. Or you can attach, for example, markers for motion track. So here you can see some markers in this cow, and then you track these specific marks. But this is labor intensive, it's time consuming. It's really hard to apply these in real life at the farm. So what we did here was we trained a model, a computer vision model using the camera system to detect 25 key points on this cow. So nose, head, neck, back, tail, head, tail, all the joints of the animal that we could see. And then we trained a model that automatically placed these key points. We used 9,000 images, was a large data set, and the performance of the model was very good. So here's the error, the Euclidean distance, which measure the error between the predicted point and the original point, which are 8 pixels distant. So it's very close. So basically, the model will do this. We place these key points representing the skeleton of the cow or the joints of the cow for these particular key points. And then we can measure, we can extract, after plugging these key points, we can extract, for example, in a segment of video, head bobbing, which is the vertical movement of the head position, which is the vertical distance between the height of the head and the width of the cow. We can get stride length, we can get tracking up, we can get all these angles of the joints, like back angle, elbow joint angle, carpus joint angle, and so on. Okay, and then by extract this from the video, we then classify the mobility score. So we had 204 cows, and then we collect 204 video clips of each individual cow. We then classify the cows with score good, 0, 1, 2, and 3, and we had to combine the score 2 and 3 because we have very few cases of score 3. So 2 and 3 was, unfortunately, we had to combine those. And then I won't go into detail how we did all the training validation, but we were very careful on not having data leakage in terms of having the same cow in the training set, on the testing set, or things like this. We try to be as independent as possible, and I can go in detail here later if that's necessary. So we found an accuracy to classify a score 0 of 83%, score 1, 74.9, and 2 and 3 mobility scores, 83.2%. So when you look at the specificity, they were good. The sensitivity was a little low for a score, mobility score 1 was 60, close to 60%. And the reason is it's really hard to get this 1 mobility score because it's almost like a health cow. So the model had a little trouble discriminating these as a sick animal. But overall, the performance of the animal was very good, very impressive. Here's an illustration of a cow with mobility score 0, consider a 0 with a good mobility. And here's the cow walking, and that's what the model is doing. The back end is basically placing these and measuring head position, head bobbing, and other features. Okay, So here's mobility score 1, which is, as I said, is difficult to differentiate from the 0. Here's mobility score 2, so you can see already a cow that's not walking very well, and you see head position, head bobbing much higher compared to a cow that was healthier, classified as 0. And this is a mobility score 3, and the cow head bobbing is much higher, back curvature changed compared to the other ones. And here you can see, for example, head bob 4.8. In the first cow, this was 0.5. So you can see it's a big change, and this being captured by the system. The problem is, this side view will create a lot of occlusion. So you have multiple cows walking and blocking each other, so you won't be able to see all the cows. So this is a limitation of the side view. In cows, they don't walk straight. That's something, that we learn. And especially the guys with more computational skills in the lab, they were somehow frustrated when they saw that. But also they are very smart guys, and they came up with a new solution, say, okay, let's do top-down view. And with top-down view, we don't have occlusion, and we don't have interaction with the animal and the device. And so now let's map 7 key points in the back of the cow. And as the cow moves, we track these key points, and we do the same, but now with the top-down view. So they're pretty smart guys. And so that's what we did here. We then map these key points, and we start collecting the neck angle, back angle, hip angle, but from a different perspective. And then we use these features to then classify mobility score. So here, before I play the video, I want to show you, this is a good mobility score, a 0 mobility score. That's this is the X coordinate in the image. That's the Y coordinate in the image. So you see cows walking very straight in all 7 key points. And then when the cow has a bad mobility score, score 3, you see that these key points will be some sort of wave, which will be the cow moving the ramp quite a lot because of the locomotion problem. So I will show you these top graphs here. So here's the cow walking very quick and straight. So walking speed is actually very important. And here is the cow. Look at the ramp of the cow here. This region will go left hand side, and this lateral movement is creating these waves that you see here in this graph, while the healthier cow mobility score 0, the cow will walk more as a straight line. So I can just play that back, and you see here. So here's the good cow, mobility score 0, and then you see in the sequence the cow with a lateral movement of the ramp that creates those waves, and these are probably the best predictors we found. So performance of these models were very similar to the side view. As you look, accuracy of score 0, 1, and 2, and 3. And again, difficult to classify score 1, but very good to classify score 2 and 3. And performed really well compared to the side view, which is very interesting, very promising, because now we can do this in large scale. We can scan thousands of cows and then classify the score, the mobility score of these cows. And as I mentioned, the back lateral, the back lateral movement was the most important variable in the model, and it was clear in the video that that was the case. So as a final consideration, we've seen that digital technologies are crucial to collect cheaper, precise, and real-time phenotypes. Collecting animal level information will be extremely important to be integrated with economics, feed management, to be used by geneticists for genetic improvement. I have collaborated with geneticists, and I know they are very interested in the animal level information that can be collected in large scale. We definitely should leverage AI systems in dairy and beef, so we can not only answer new questions, but also some older questions that we'll never answer before, because we're not able to measure some of the things we can measure now. And this is a very nice area. There is a lot of interest of this new generation of students and professionals that want to learn about the technology and use the technology to address biological questions related to animal growth, animal health, genetics, and this being a very pleasure place to be and to work, area to be in working now. I would like to acknowledge USDA for funding most of these trials that I showed, their Innovation Hub, Data Science Institute, WRF, High Throughput Computing have used a lot of computational resource out there, Microsoft for funding research in our lab as well. And of course, this amazing group, these are the guys developing all the trials I presented today. So a big thank you to them. And with that, I'll be happy to answer questions. Thank you so much.
Yes, thank you. Wow, what a great presentation and so insightful indeed. Now we're going to open up a short time for questions.
Yeah, you want me to jump in here, Angie?
Yeah, that sounds great.
All right. So, first question in the Q&A. Thanks. You make technology sound so easy. Do you have any plans to check cow behavior in holding areas related to the use of crowd gates and welfare?
Yeah, that's a good point. I remember talking to Dr. Jennifer Van Hoos and Dr. Katie. We have a student working with robotic systems, and there was this discussion about, looking to, for example, I'm taking your question to automatic milking systems and looking for how animals are waiting for other animals inside the robot, and this could be used for any other regions where you have crowded space and animals with problems related to welfare or in holding pens or in holding areas. and also to check behavior for high stocking density could also be used. We have not done, to directly answer your question, research on that particular problem, but there is, tremendous opportunity there for sure.
Oh, good question. And definitely a lot of possibilities, right? Going back to maybe closer to the beginning of your presentation, a couple questions on with identifying the animals by the color pattern. Are you able to pair that with EID readers as well? And we'll start with that. And then a couple follow-up questions related to that.
Mm-hmm. Yes. So yeah, of course. I mean, the RFID is still the most used, identification technology. Combining this with the camera, it can definitely improve reliability of the system. It could make the system even more robust. I guess what we're trying to accomplish in the trials that I demonstrated was how would be the performance without any other sensors informing us about the ID of the animal, and completely using computer vision and not any other thing. And the reason we try to do that is that as you add and combine more technology, you can make systems more robust, but also you create other opportunities for failure, because now you have two technologies being combined. And if you want, it's just another layer to manage at the farm. It creates more robustness in terms of if one fail, you have the other one. If the other one fail, you have the other one. But connecting those and making them to work together, sometimes it creates another layer. But I agree that RFID is the most used, and in our case, the computer vision was the attempt to see how this would perform if I only have that technology out there.
No, that makes sense. I think, and related to that, do you have plans or thoughts on how this might be integrated with current herd record keeping software? And also a question on herd size. Is there any scaling to this, or all herd sizes should be looking at something like this?
Yeah, that's a very good question, and they come very often related to, is the small farmer able to use that? The camera system and how we use those, in my opinion, for the examples I showed here, it doesn't really matter the herd size. If you have 30 cows, 100 cows, you may just not need some of this technology because you're able to watch all of them and know all of them, and so you may don't want to pay for them. But then if you have 300 cows or 500 cows, you may be able to look at those cows individually, and then there is no difference from 300 cows that you cannot watch individually and 3,000 cows that you can also not watch individually. And if you have a camera installed at the axis of the parlor, this will work for these 300 cows or these 3,000 cows. Of course, you're going to dilute more the cost of investment if you have 3,000 cows, because you still have two lanes where the cows will leave the parlor. Now, at some point, someone with more cows will need to buy more cameras, and the cost will scale up for more cows too. And so I guess it depends the technology, but overall, the computer vision, because you have one camera that monitor multiple cows, it's usually how can I say that, is usually positive for smaller and larger farms in terms of adoption. But this is a good question. This is something we have a grant right now. We are evaluating, we are investigating the economic impact of this technology, the capacity of them to be scaled, and also which one would be a good fit for larger or smaller. But it's a difficult answer to address for all technology. But for the computer vision particularly, I see positive adoption for small farms and for large farms.
Obviously you've had some time to think about this and see some of these questions, other presentations, but it's really interesting. So this one I'm going to read closely because it's very specific to some of the cow health monitoring that you previously talked about. So 2 questions. Is there a reason BHB cutoff was at 1? And 2, did the prediction work to find cows above the cutoff point? But did you consider also postpartum performance, milk production, reproductive performance after the fact?
Yes, very good question. Yes, so there was a reason. We initially want to use 1.2. I guess probably the most common threshold cutoff report in the literature, 1.2 millimoles. The problem is we have about 100 cows in this trial. It was a very time-consuming trial because we had to collect blood samples every other day and plus a lot of other things. And we couldn't do that in a much larger scale than we have done. And what happened that we did not use 1.2 is that as we use 1.2, the number of cows above the threshold was not super high, which means that the model would be super unbalanced to be training. So for example, I don't know the numbers top of my head, but let's say if I have 100 cows, I would have maybe 80 cows consider healthy and only 20 above 1.2. Let's put this way. I'm not saying this is not the number, I don't remember, but when I say unbalanced, is very few cows above the threshold. And because 1.0 is also used as a threshold, as a cutoff, we use 1.0, then we had more cows above the threshold, so the model was more balanced to be trained. And it became a more conservative model because, a cow may be 1.0 and not 1.2, may not, be considered subclinical ketose for people using 1.2 as a cutoff. And so you can look at it as a more conservative model that will flag a cow that is like, in this borderline a little bit about 1.0. And so, but the main reason was if we use 1.2, we have very few cows. 1.0 make the model more balanced. And so for training the model and testing these hypotheses, and because 1.0 is accepted, then we adopt 1.0. And your second question is related to if you consider postpartum performance, not for we only use postpartum performance for the cows for previous lactation, right? So we didn't want to use the performance of the cow postpartum because we are using all the variables to predict the subclinical ketose prepartum. So then that's the reason. So that's why I could not use the postpartum, because all the variables should be obtained prepartum. Now, if the performance was related to previous lactation, then it was part of the prepartum inputs, and then we used some of this information in the model, yes, which we call cow history, but it was the information from previous lactation, including healthy events.
Oh, good, thank you. A general question that came up a couple of times throughout. Do you have a prediction or sense of how close to commercially available a technology like this would be? Obviously, the algorithms are proprietary, how that process might work to make this available on a wider scale?
Yeah, that's a good question too. I guess there is a lot of interest in the industry. The industry is trying to develop technology on that space. Sometimes they are kind of protective, from how they want to collaborate or develop or co-develop. What we do here at the university is we do our research. We try to address the questions we have. We develop the technology. Some of this technology get patented by WRF, which is the Wisconsin Alumni Research Foundation on campus. Some of this technology, they are not interested in patent. We always publish the trials we have, so this is all out there. And so the industry and companies, they can get information, they can get how the models were developed or training, how we implement the technology. These are all in the papers. And so they can get these and convert these into a commercial product and make progress. But these will be way more on the hands of the industry than the academia to convert these into products and to basically put these to work at the field. That's my vision.
Well, this was great, Dr. Dorea, to think of all the possibilities and how the difference of what our cow eyes tell us when we're looking at animal behavior and what the cameras show, and just the natural way cows progress through their lives, and you would have that snapshot. It's very interesting. And with no other further questions, I would like to remind all the attendees that we did record this, and we will have it out to everyone that registered within a week's time. And then, as always, if there's any other questions that you can think of or that you'd like to ask, please contact either of us or Dr. João, and we'll get you the answers. So I hope you enjoyed today's webinar. I'd like to invite everyone next month on August 20th for Cows Need Fiber 2, Storage and Feeding Tips to minimize nutrient loss. We're going to have two speakers next month, Dr. Louise, and then also Jackie McCarville, who is a regional dairy educator, and they're going to talk a little bit about the potential costs of dry matter and nutrient losses occurring during silage, and strategies to mitigate that issue. So that's more of a nutrition topic next month. And then, as always, if you ever are looking for any information or unbiased university-based research, please take a look at our Extension Dairy program on the web or find us on Facebook at Extension Agriculture. So with that, thank you everyone for attending.
Thank you very much. Thank you again, Ryan and Angie for the invitation. Thank you all.
Thank you.
Yeah, thank you. Great job.